Welcome back, everybody. Mr. Johnson with you once again. This is Lecture 20 on Lewis structure diagrams, section 6.5 in our book. We're on page 357 of our textbook. But before we dive more into the book, I'm going to take you to the whiteboard to share with you the storyline or the progression of concepts or skills that will be revealed to you over the next few lectures. And there's great coherency into this storyline and into how these skills connect, so I thought I'd start with that. So the first part of this story is what today's lecture is primarily about, which is to go from the formula of a molecule, a molecular compound comprised of nonmetals that are sharing electrons, to what's called the Lewis structure. And this depicts that. Going from NH3 to the way that this is drawn is going from the formula to a Lewis structure. And again, that's what today's lecture is primarily about. Once we know what the Lewis structure is of a molecule, we are then able to predict its shape. And that's what the lectures following this one are about, is the VSEPR theory, which allows you to predict the shapes, the three-dimensional shapes of molecules based on their Lewis structure. And NH3, or ammonia, has a trigonal pyramidal shape, which you'll learn how to predict, again, in the next several lectures. Once we know the shape of the molecule, we're able to, by looking at whether or not its bonds are polar, which will be taught to you, and looking at the symmetry or asymmetry of a molecule, predict whether or not that molecule is polar. So once we know what the shape of a molecule is, we can predict whether or not it's polar. And ammonia is polar because it has polar bonds and it's asymmetrical. And I'll teach you that later. Once we know whether or not a molecule is polar and some other features about it, we can determine its intermolecular forces, the kinds of forces that exist between the molecules, intermolecular forces, forces between molecules. And the type of intermolecular force that ammonia exhibits, or ammonia molecules exhibit with other ammonia molecules, is what's called hydrogen bonding. It's a poor name for an intermolecular force because it isn't a true bond. And then once we know the type and strength of the intermolecular force, we're able to predict all sorts of physical properties or compare the physical properties of molecules to others. And ammonia, for example, based on its structure and polarity and intermolecular force type, is soluble in water. It's something you'd be able to predict in the future. It has a relatively high boiling point and some other aspects as well about it you could predict. So that's the storyline over the next several lectures, and it is a doozy, as they say, somewhere. Not sure where. So we're back to our book in section 6.5, page 357 of our textbook, and I'm going to scroll down to the bottom of this page where we see this important table reminding us of how the placement that an element has on the periodic table tells us, due to the patterns we know exist in electron configurations, how many valence electrons those elements have, which is crucial to drawing a Lewis structure you'll see here in a moment. It's reminding us that groups 1 and 2, the first two columns on the periodic table, have 1 and 2 valence electrons respectively, and then groups 13, 14, 15, 16, 17, and 18, the last 6 columns, have 3 through 8 valence electrons respectively, and this is reminding us of the pattern in their electron configurations. If we go to the whiteboard, we can see that that's something we know as well. In this column, all the elements have 1 valence electron. These all have 2. Remember that all the transition elements have 2 because they always have the outermost S sublevel full of 2 electrons before they fill the D, and then 3, 4, 5, 6, 7, and 8. Because Lewis structures are focused primarily on molecules comprised of nonmetals sharing electrons, it's really these columns whose valence electrons we need to be paying attention to. So there we go. That's how we predict how many valence electrons elements have, because that is the first step we'll find in this 5-step process for drawing Lewis structures. So I've flipped the page. I'm now on page 358 of the textbook, and we're looking at this table here, which is a periodic table of the first three rows. What these are the Lewis structures of individual atoms, or the Lewis structures of an individual atom for an element. While this lecture is primarily about drawing Lewis structures for molecules, you could be asked to draw the Lewis structure for an individual atom. All that involves is putting as many dots around the symbol of the atom as there are valence electrons. And as you know, every element in group 1 has just 1 valence electron, so there's just 1 dot. All the elements in group 2 have 2 valence electrons, and there's 2 dots. Electrons don't pair up until, as you know, there's at least 1 electron in every orbital, so we're depicting these electrons being unpaired by having electrons on sides by themselves. Here is boron and aluminum with 3 valence electrons, carbon and silicon with 4, and then when we get to nitrogen and phosphorus, once there's 1 dot on each side, the electrons pair up. 5, 6, 7, and 8 valence electrons. Helium is an exception to the noble gases. Helium has a full valence shell with 2 electrons because it only has the first energy level, which is full with 2, whereas neon and argon are full with 8. We refer to elements having a full valence shell as having a full octet, meaning 8 valence electrons. That's not true for hydrogen and helium, which are full with just 2. So these are the Lewis structures of individual atoms, where the dots depict the number of valence electrons, and 1 dot goes on each side before they pair up. Some really important points here in this figure that's highlighted in blue, green, and orange. The first being that each element in a family we already talked about has the same number of dots because they have the same number of valence electrons. And as you go across a row, of course, the number of dots increases, as does the number of valence electrons. For metals, which this lecture is primarily not about, the number of dots tends to reflect how many valence electrons will be lost when that metal forms an ionic bond with a nonmetal. It's how many valence electrons are lost, and it's also what the positive charge will be. For nonmetals, which can either gain electrons in an ionic bond from metal, the number of unpaired electrons reflects how many electrons would be gained. Fluorine and chlorine, for example, have just 1 unpaired electron and are likely to gain just 1 electron to get to 8 and to form 1- ions. The number of unpaired electrons, which is more relevant to this lecture, also reflects how many valence electrons that element will share to get to a full valence shell. Fluorine and chlorine each have 1 unpaired electron. They share just 1 electron to get to a full shell. They only form single bonds. Oxygen and sulfur, though, notice, have 2 unpaired electrons. They form 2 bonds, covalent bonds, to get a full shell, which means they can either form 2 single bonds or a double bond. As we scroll down, we're looking at figure 652. This is showing the Lewis structure for an ionic compound, which is something that is typically taught coming into this class, where the metal, because it's an ionic bond, is losing a valence electron to the nonmetal. And in sodium's case, it loses just 1 valence electron. When sodium is drawn as an ion, it is depicted without any valence electrons. That's a convention for Lewis structures for ionic compounds. It's then placed in a bracket, and its charge, having lost 1 valence electron, is placed in the upper right-hand corner as a plus or a 1+ charge. The nonmetal is shown as having gained the metal's valence electron or electrons. In this case, chlorine with 7 gained 1 from sodium. So it is shown with a full valence shell with a full octet, the nonmetal. It's in brackets as well, and having gained a negative electron, it's a 1- ion. So that's something you could be asked to do in here, but is less likely than, again, what it is I'm about to teach you. Lewis structures for molecules. Coming your way finally. Rather than teaching this next section out of the book, I'm going to be using PowerPoint slides that I embedded into this little whiteboard scenario here. And I've reduced and simplified the steps in our book to these 5 steps, and I hope that this will prove to be effective for you. There's 5 overall steps that we will use to be drawing Lewis structures from the formula for a molecule. And here they are. I just thought it would be nice for you to see all 5 steps together, because in a moment we're going to see the steps broken up. We'll do them one at a time together and come back to this complete set of steps in the end. Here they are. If you want to pause and just take a peek at these steps before you see them revealed to you one at a time, you might consider doing so. So the first step, like we saw above or a moment ago, is to determine the total number of valence electrons available to build the Lewis structure from in all the atoms of the molecule. And we'll use NH3, ammonia, this was in the intro to this lecture, and carbon dioxide as examples. So we need to go to a periodic table to find out which column N and H are in, and based on the column they're in, that'll tell us how many valence electrons they each have, and we'll add them up. We'll do the same for carbon and oxygen as well. All right, here we are back at our periodic table. Nitrogen in column 5 has 5 valence electrons, and hydrogen in column 1 has just 1. So nitrogen and hydrogen have 5 and 1 valence electrons respectively. Carbon has 4, oxygen has 6. So let's remember those numbers as we go back to the example. So let's write those numbers in to keep track. Nitrogen, we said, had 5. Hydrogen has 1, but there's 3 hydrogens. So each hydrogen contributing 1 valence electron means there'll be 3 from the 3 together. And 5 plus 3 is 8. Ammonia, or NH3, has 8 valence electrons available to build the Lewis structure from. Carbon, if you recollect, had 4. Each oxygen had 6. There's 2 oxygens, and 4 and 12 is 16. So we have 16 electrons to play with to build carbon dioxide's Lewis structure from. So again, 8 valence electrons from ammonia, 16 from carbon dioxide. Step 2 is to construct the skeleton. The skeleton by determining the central atom and then connecting all the atoms, the remaining atoms, to the central atom via single bonds at first. They might become double or triple bonds later. We build the skeleton with single bonds at first. The central atom can be determined one of three ways. It's almost always the first element written. In this case, that would be nitrogen or carbon. There's typically only one central atom. So there's only one nitrogen. There's only one carbon. That's another way we would know it's central. The best way is that the central atom always has the lowest electronegativity of all the elements in the compound. And nitrogen has a lower electronegativity than hydrogen. So does carbon have a lower electronegativity than oxygen. So nitrogen will be central, carbon will be central. So we draw the symbols, and then we connect the central atom to the other atoms via single bonds at first. They may become double later. For now, we have them as single. And here is the skeleton for carbon dioxide. We have just built the skeletons for ammonia and carbon dioxide by having determined the central atom and connecting that central atom to the other atoms, what I'll call the peripheral atoms, or the outside atoms, at first via single bonds. The next thing we do is to subtract the number of electrons that were used to build the skeleton from the total number of valence electrons that were available from step 1 to determine how many valence electrons remain to build the skeleton from. The skeleton, remember, is comprised of single bonds. A single bond represents the sharing of 2 electrons. So each single bond that's drawn in a skeleton represents 2 electrons. In NH3, 3 bonds were drawn. That's 6 electrons that were depicted via those 3 single bonds. So if we do 8 valence electrons from step 1 that were available minus 6 that were drawn, there's 2 left to build the Lewis structure from. In carbon dioxide's case, there were 16 available to begin with, minus the 4 that were drawn from that skeleton, 2 bonds, 2 electrons, 4 total. 16 minus 4 is 12 left. All right, step 4 is a little more involved. Step 4 says to first place the remaining electrons as lone pairs. These are non-bonding electrons. They'll show up as pairs on the edges of the symbols. On the peripheral atoms, to give each peripheral atom a full octet. Now remember, all atoms except hydrogen and helium achieve a full octet through 8 electrons. Hydrogen is full with 2. Once hydrogen has a single bond connected to it, those are the 2 electrons that hydrogen needs to be stable. So hydrogen with a single bond is stable. It never needs extra electrons. We will never put lone pairs on hydrogen because, again, they're already stable. Hydrogen has achieved its octet in this left-hand diagram. So then it says if there's electrons remaining, place these on the central atom to achieve a full octet. Well, there are 2 electrons left over to draw. The outside atoms can't have any, so I now draw these 2 electrons as a lone pair on the central atom. I have no choice but to put them there. And in so doing, I've run out of electrons. I already know that the hydrogen atoms on the outside have their octet or their duet, and now the nitrogen atom in the middle feels like it has 2, another 2, another 2, and another 2, or 8 electrons. The 3 single bonds give nitrogen 6 electrons total, and the lone pair gives it another 2 electrons. Nitrogen now has its octet. This is a complete Lewis structure for for ammonia. As we go over to carbon dioxide, same thing. We will place the remaining electrons as lone pairs on the peripheral atoms to give them an octet. I've got 12 left. Each oxygen right now has only 1 single bond. That's 2 electrons, and an octet is 8, so I can put 6 lone pairs on each oxygen. In fact, you can always, as long as you have enough electrons, put 3 lone pairs or 6 electrons on peripheral atoms to give them an octet, except hydrogen, as you know. I've just drawn 6. And I give the other oxygen a full octet, which is achieved with 6 electrons. I've drawn 12 electrons. I have run out of electrons. So now we go to 4b. If after running out of electrons, the peripheral atom or the central atom does not have an octet, then we move lone pairs from the peripheral atom to an additional bonding pair. Let's acknowledge that the peripheral atoms, the oxygens, do have an octet, but carbon in the middle does not. That's a problem. We need carbon to have an octet. So what we're about to do is move a lone pair from one of the oxygens to an additional bond. So I'm going to erase these top 2 dots and turn them into a second bond. What that does is keeps oxygen with its octet, because the oxygen atom on the left-hand side still has 4 electrons from the 2 lone pairs and 4 more electrons from the 2 bonding pairs. The oxygen on the left has an octet. The carbon now has gained 2 electrons. By moving a lone pair into a bonding pair, it gives the central atom 2 more electrons than it had and keeps the peripheral atom with the same number. Carbon in the middle has 6 electrons. It's closer to 8 than it was. We now, instead of moving a lone pair from the left-hand oxygen atom to another bonding pair, want to do it to the other side for a reason that will be told to you later. So we do the same thing on the right-hand side, erase that lone pair, turn it into a bonding pair. That doesn't change the octet for oxygen, but it gives carbon the central atom and octet, because with 4 bonds times 2 electrons per bond, carbon has a full valence shell, or a complete octet. So there is carbon dioxide's Lewis structure. It's a double bond between the carbon and each oxygen with 2 lone pairs on each peripheral oxygen. And to the left is ammonia's Lewis structure, where the nitrogen has 3 single bonds, each to hydrogens, and 1 lone pair. Before we go to step 5, I thought we'd do 3 examples using those 4 steps you were just taught. If you want to try these on your own, you may. If you want to walk through them with me, that's fine as well. So we're going to do these 3 right now. All right, boron I know is in column 3 of the periodic table. It has 3 valence electrons. The first step, remember, is to calculate the total number of valence electrons available in all the atoms of the molecule. Chlorine, meanwhile, has 7. 3 plus 3 times 7 is 24. And I'll do each step for all 3 molecules at the same time. Carbon has 4. Each hydrogen has 1. 2 times 1. Oxygen has 6. 4 plus 2 plus 6 is 12. Hydrogen has 1. Carbon has 4. Nitrogen has 5. 1 plus 4 plus 5 is 10. So step 1 is to find the number of valence electrons available to build the Lewis structures from, and we've done that for all 3 molecules. Step 2 is to build the skeleton by determining the central atom and hooking it up to the peripheral atoms via single bonds at first. Boron, because it's written first, and there's only 1 of it, and it's less electronegative than chlorine, will be central, and I hook it to chlorine via single bonds at first. Carbon is also written first. It's the least electronegative element, and carbon is almost always central anytime it's in a molecule anyway. So carbon, for a lot of reasons, will be central. I hook it to the 2 hydrogens and the oxygen via single bonds at first. Here's HCN. Here is an exception to the first element typically being central. Carbon is central over hydrogen because carbon's always central when it's in a molecule, and it's less electronegative than hydrogen or nitrogen. So here's carbon with a nitrogen and a hydrogen on either side. So we've just done step 2, built the skeletons by determining the central atom and hooking it to all the peripheral atoms via single bonds. I now subtract from the number of valence electrons available from step 1, how many were just drawn via those single bonds. 24 minus 3 bonds times 2 electrons. 24 minus 6 is 18 left. 12 minus 6 is 6. And then 10 minus 4 is 6. So these numbers are how many electrons are left after having drawn the skeleton. Step 4 is to place the remaining electrons on the peripheral atoms until they have an octet, and if there's some left over, to then place them on the central atom. And if now not everyone has a full octet, to move lone pairs to bonding pairs. So step 4, again, is several steps in one. All right, so I need to draw 18 electrons. The chlorines, because they're not hydrogen, can each take 3 lone pairs, or 6 electrons to get them to 8. So there's 6, there's 12, and there are 18 electrons. I've drawn all the electrons that I can. Now in this case, I would be inclined to move a lone pair from one of the chlorines to a bonding pair to give boron an octet. But folks, boron is in the 3rd column of the periodic table, and it only has 3 valence electrons. Boron is an exception to the octet rule. Boron in a Lewis structure will be stable with just 6 valence electrons. Be okay with boron having not an octet, but rather 6 electrons and 3 single bonds. It's an exception. So is aluminum, which is technically a metal but can act like a nonmetal in some cases. Aluminum is beneath boron and is also an exception to the octet rule. The only other exception is beryllium, which is in column 2, which is a metal, but on occasion can act like a nonmetal. So if you see beryllium showing up in a Lewis structure, know that it can have just 2 bonds or 4 valence electrons because it's in column 2. So boron, Aluminum and beryllium are the exceptions to the octet, and we'll see them show up again. This Lewis structure is done for BCl3. For CH2O, though, we've got 6 electrons left. I know I never give lone pairs to the hydrogens, so I place 1, 2, 3, 4, 5, 6 on that oxygen. Oxygen has an octet, but carbon doesn't, so I move a lone pair from oxygen to a bonding pair, which doesn't change the octet for oxygen, but gives carbon the last 2 electrons it needs to have an octet. There is the Lewis structure for CH2O, also called formaldehyde. We go to HCN. I've got 6 electrons left to draw. I draw them on my peripheral atoms as lone pairs at first. Hydrogen, again, never can have lone pairs, so I go to nitrogen and give it 6 dots. Remember, peripheral atoms will get 6 dots in this step to get to 8. Nitrogen has an octet. I've run out of electrons. Carbon doesn't, so I need to move lone pairs to bonding pairs by taking away dots from nitrogen and drawing them as a line. So I do that once. Oops, that's eraser still, which maintains nitrogen's octet, but puts carbon at 6 electrons, not yet 8. So I need to do that a second time, and that will still maintain nitrogen's octet and give carbon, this central atom, an octet. So that's the Lewis structures for these 3 molecules, using steps 1 through 4. Step 5 is about expanded octet molecules, which is what a couple of the optional VSEPR lectures are about, which you could choose to watch or not choose to watch. But I do want you to be able to draw Lewis structures for expanded octet molecules. Much like there are some atoms who are stable with less than an octet, an incomplete octet, boron, aluminum, and beryllium, there are some atoms that, under circumstances, exceptional circumstances, can be stable with an expanded octet, more than 8 valence electrons. It's the halogens that do this, oxygen, fluorine, and chlorine, for reasons we'll see in a bit, and some of the noble gases will have an expanded octet, which might seem weird because we were led to believe noble gases don't bond because they already have an octet. Well, under, again, strange circumstances, noble gases can be forced to form bonds, and when they do so, they can end up with an expanded octet. You don't really need to worry about which elements can or cannot have expanded octets. Rather, if you get to a point in building Lewis structures where step 5 has to come into play, which I'll model for you in a moment, imagine that whatever atom is in that Lewis structure can have an expanded octet. So just let the rules play out, and some atoms will end up with expanded octets. So step 1 is to count the valence electrons. Xenon is a noble gas. It's got 8 valence electrons. Fluorine is a halogen. It's a group 7. It's got 7. 4 times 7 is 28, plus 8 is 36 electrons to play with. Xenon is going to be the central atom because it's left of fluorine and has a lower electronegativity because it's frankly 0. I hook it to the fluorines with nothing but single bonds at first. I've built its skeleton. I now subtract from 36 the number of electrons that were just drawn via bonds. 36 minus 8 is 28. So I have 28 more electrons to build this Lewis structure from. And I'm going to erase that so I have room above fluorine to give it some lone pairs. So 28 electrons is what we have to play with. I put those electrons as lone pairs on the peripheral atoms at first, knowing that I normally put 6 dots on peripheral atoms unless it's hydrogen. So I'm going to slap 6 electrons on all the fluorines, and that's 24 electrons. Remember, I had 28 to play with, so I've got 4 more to draw. Again, I had 28 to play with. I've just drawn 24, and everybody has an octet. So in this case, I draw the additional electrons, the 4 additional electrons, as lone pairs on the central atom. And that means that I give xenon 2 additional lone pairs, or 4 additional electrons, to get to that 28 that I needed to. The only choice was to give xenon an expanded octet. Only central atoms will end up with expanded octets. All right, let's try chlorine, trifluoride, in red this time. Chlorine will be the central atom because there's only one of it, and it is less electronegative than fluorine. It's below it on the periodic table. So I build the skeleton. Ooh, I just got ahead of myself. That's okay. I know I need to anyways. I'll go back and count valence electrons. These are all halogens. They're all in the 7th row. They all have 7 valence electrons. 7 and 21 is 28. And then 28 minus the 6 electrons I drew via the 3 single bonds. 28 minus 6 is 22. So I have 22 electrons to play with here. I'll place these 22 remaining electrons as lone pairs on my peripheral atoms first. And that's 6 that I put on all atoms but hydrogen, which gets me to 18. So I've drawn 18 electrons. I know when I have remaining electrons which there are 4 of remaining. I put them on the central atom until it has an octet. Putting 2 dots on chlorine gives chlorine an octet, but I've only drawn 2 of the remaining 4 electrons, not all 4. So if everybody has a full octet and there's extra electrons, which there are 2, you give the central atom an expanded octet, and in this case, that means giving chlorine a second lone pair. So in this case, chlorine as the central atom feels like it has 10 valence electrons or an expanded octet. Look at the pretty green and the pretty red. All right, getting close to the end here. Last thing I want to talk with you about is how we draw Lewis structures for polyatomic ions and this thing that our book calls the curious case of resonance, what resonance is. All right, so NH4, ammonium, is a polyatomic ion. And you may recollect from the beginning of the year, we talked about how polyatomic ions are really like molecules, except that they've gained or lost an electron in order to form, and then have a charge and also have an ionic bond with another oppositely charged ion. So we're about to draw the structure of just this ammonium ion, knowing that it can only have formed if it lost 1 valence electron total to something that ends up being the negative ion that it forms an ionic bond with. So we're drawing again the structure of just the ammonium ion, knowing that it's a part of a larger ionic compound. Well, we count valence electrons. Step 1. Nitrogen has 5. Each hydrogen has 1. And 5 plus 4 is 9. But then we have to account for the charge on the ion and the loss or the gain of an electron. Well, a 1 plus ion is positively charged because it's lost an electron. So rather than having 9 electrons, this ion, when it formed, for it to form, has lost 1. Oops, 9 minus 1 is 8. So there's 8 valence electrons that in ammonium we have to build the Lewis structure from because, again, it lost 1 of its 9 electrons. I then build the skeleton by connecting nitrogen, the central atom, to each of the 4 hydrogens. And in so doing, I've drawn 8 valence electrons. I subtract the 8 electrons I just drew from how many are available to me. 8 minus 8 is 0. There's no more valence electrons to play with. And everybody has an octet. The hydrogens have their 1 bond they want, and the nitrogen has 4 bonds or 8 electrons. This is a stable or a complete Lewis structure, except that the convention for polyatomic ions is to put them in brackets, kind of like we saw the monatomic ions, sodium chloride earlier in our lecture, being in a bracket, and its charge in the upper right-hand corner. So whenever you ask to draw a Lewis structure for a polyatomic ion, know that it can't exist on its own. It's existing in an ionic compound, but that when we draw it by itself. We account for the gain or loss of electrons or electron, put it in brackets, and put its charge in the upper right-hand corner. So we'll now do it for carbon dioxide as a chance to practice this and as a chance to talk about this thing called resonance. Carbon has 4 valence electrons. Each of the oxygens have 6. 4 plus 18 is 22. But it's a negative ion, which means that it has gained 2 electrons in forming. So if I add 2 to 22, I get 24. I'm now going to build carbon dioxide's skeleton. So I put carbon in the middle and each of the 3 oxygens connected to the carbon via single bonds. I now subtract from 24 the number of electrons that were drawn via the skeleton, which is 6. And I have 18 electrons left to play with or build my Lewis structure from. I place them as lone pairs on the peripheral atoms. There are 6. 6 more is 12. And 6 more is 18. I've run out of valence electrons. The peripheral atoms have an octet. Carbon doesn't, so I have no choice but to move one of the lone pairs on one of the oxygens to carbon. Now, this is where this thing about resonance arises. If it's an even choice. If it's an equal choice, which atom to move the lone pair from, because all 3 oxygens are the same, then it doesn't matter which one you move it from, except that it's misleading. So let's move it and then talk about resonance. So I get rid of 1 lone pair. Again, it could have been any lone pair on any oxygen, and turn it into a bonding pair, which gives the carbon, the central atom, an octet, and maintained the octet that was on that lower oxygen atom. There would be carbon dioxide's Lewis structure, if it weren't for resonance, which again we'll talk about in a moment. And because it's a polyatomic ion, I said carbon dioxide, I meant to say carbonate. Because it's a polyatomic ion, I put it in brackets and put its charge on the outside. So there it is again without resonance, which we'll talk about and will be the last thing we talk about today. Like we mentioned a moment ago, there were 3 options for which of the oxygen atoms could have its lone pair turned into a bonding pair. These are the three Lewis structures that depict those three options. The reality is that all three options exist simultaneously. All three oxygen atoms on the periphery have their lone pairs being turned into a bonding pair. But what's really more accurate is to say that not any one oxygen donates its lone pair to a bonding pair, but all three do so all at the same time. And so what ends up happening is not that there's two single bonds and a double bond, but rather that, and I'm going to draw the skeleton here, each of those single bonds is a 1 1/3 bond. Instead of that double bond being on one of the oxygens and singles on the other, those double bonding electrons get shared evenly amongst all three single bonds, and so we draw it kind of like a dotted line, suggesting that double bond is actually in all three places at the same time. It's not a single bond, it's not a double bond, it's what we could mathematically call a 1 1/3 bond. When there's more than one option for where you think the double bond should be, because the peripheral atoms are the same type, when the molecule's symmetrical, except for the placement of the double bond, then that double bond is shared evenly amongst all the atoms and creates what's called resonance. It's weird, but it exists. What's significant about this is that there's not a double bond and two single bonds. In carbonate, there aren't two bonds that are longer than the other bond, because remember, single bonds are longer than the double bond. Rather, in carbonate, all three bonds are the same length as each other, they are all the same strength of each other, and they are shorter and stronger than a single bond, because it's a 1 1/3 bond, but they're all longer and weaker than a double bond. So hopefully that gives you some insight into resonance, and we're going to see how it shows up later in other molecules. It accounts for a lot of important things about chemistry and about nature that we'll talk about later. And if you want to read about that, because what I said didn't make that much sense, on page 367, the middle of 367, is an explanation about resonance that hopefully aligns with what I said, but might be depicted a little bit differently. That is the end of lecture 20, folks. Thanks for hanging in there with me. Hopefully that made sense. I find drawing Lewis structures great fun, and I hope you do as well. The next couple of lectures about VSEPR will be the next step of the story, which is once we've learned how to draw Lewis structures, how we can predict their shape in nature, their three-dimensional shape. They're going to come to you from Tyler DeWitt from the internet, partly because you might like to hear from someone other than me, and I didn't bring all my molecular models home from school, and I wanted you to see someone who had these 3D models to be able to show you and manipulate and help you make sense of this. So enjoy the next couple of lectures, and I'll see you again for the polarity of molecules in a little bit. Take care.